All right, so most of the reason I'm making these talks is just to alert you to the whole world there is to study here. Certainly I haven't said enough about most anything in here to really understand it. The only way you can really understand it is to, get a copy of TAP and just work out the exercises for yourself, right? That's what you got to do. But I hope we can get a big picture of what's some of the ideas here and what's going on. This chapter in particular is very, very interesting, what we learn. And I hope you can get some intuitive sense for it as we cover it. So anyway, so SON, SUN, UN, and SPN are all basically, when you boil it right down, simultaneous rotations in a collection of orthogonal planes. This geometry is revealed through the study of the maximal torus. The maximal torus essentially contains the angles of those rotations. All right? So the first order of business is define the torus and prove that the tori are the only path-connected compact abelian matrix groups. Definition. What is the n torus? Well, the n torus is the direct product of u1, u1, and u1, and u1 n times, n full times, Tn. This is naturally isomorphic to the diagonal matrices which are diagonal and have just imaginary exponentials on the diagonal. So this is naturally found with this particular kind of diagonal matrix, which is in itself in the n by n invertible complex matrices. All right. So if we want a nice model of Tn, this is a nice go-to model for the n torus. And so here's a proposition for you. If we have a basis for Rn, then the quotient group, so you take the abelian group of Rn with respect to addition, and mod by the group generated by z linear combinations of integer linear combinations of that basis, v1 through vn. This is isomorphic to the n torus, and here this is just again an integer linear combination of the basis, lattice, right? It's an n-dimensional lattice. So the proof of that assertion is given here. If we have f defined as such, f of t1 to tn is the diagonal e to the 2 pi I t1 e to the 2 pi I tn, right? So here's a mapping into that particular kind of invertible n by n complex matrix. That's certainly a surjective homomorphism from the Euclidean n space with respect to addition and the n torus as seen inside GLNC. All right, as a model for the n torus, if you wish. I'm just going to call it the n torus. So let's just take as granted that this is in the n torus. All right, because I'm getting tired of calling it the model of the n torus, I'm just going to call it the n torus. All right. Anyway, granted that's a slight abuse. Now, the kernel of, and to prove that's a homomorphism, I mean, if I have t1 plus s1, then I get t1 plus s1 up here, but then the exponential gives me, e to the 2 pi I t1 times e to the 2 pi I s1. And the same on each and every entry if I, do an addition here. And then because they're diagonal matrices, I can write the, product of the diagonals. I mean, it's a simple exercise to prove that this is a homomorphism property. I mean, there's something to prove there, but you can do it. It's not hard. So anyway, the kernel of this mapping is what? Well, it's exactly E1 through En, right? Well, why is that? Why? I guess my question is, why is it just that? Oh, this is integer linear combinations of these. Remember this notation, it's like, certainly if I have a 1 or a 2 or a, well, kernel of f, so this has to be equal to what? Oh, not to 0, this has to be equal to, Oh, goodness gracious. Kernel of f is all the t1 through tn such that f maps to the identity. The identity here is the identity matrix, in fact, which would make every one of these arguments to be 1. How do you get e to the 2 pi I times t1 equal to 1? I suppose you need, well, t1 equal to 0, tn equal to 0 certainly does it, right? And it claims it's just this. I don't know, for some reason I'm not seeing it right off. I think this is the standard basis, right? Yeah. All right, well, I'm gonna move on. I think it's not hard. I'm having some mental block here to proving the assertion that that's the kernel of this map. I think it is. Anyway, so Tn, once you've got that, then of course this mod its kernel. If this is the kernel, then the group mod the kernel. That gives us Tn. There's some details I'm a little slippery on right here. Anyway, now we need to extend this result to any basis. So this, I guess this is, I'm arguing that this is good for the standard basis, but we need to extend it. We need to prove the result for an arbitrary basis. So if I have A in an invertible matrix such that the multiplication by A takes me from the standard basis to this other basis VI, and then of course RA goes from Rn to Rn as an isomorphism, which maps the standard basis to the non-standard basis, and hence the quotient is isomorphic to the other quotient, which gives us then this characterization of the torus as this quotient of Euclidean space by a lattice. Now, if we have these vectors v1 through vk and Rn, if they're linearly independent, then if you quotient by a lattice, and so k doesn't have to be n, like we just did it for the full dimension. So here is like for less dimension, k could be less than n. So something's left over, right? And so you get a k torus, and then whatever's left, you get a Rn minus k piece sitting here. So that's what would happen if you didn't mod out by the full lattice. Theorem 9.5. Any compact abelian path-connected matrix group is isomorphic to a torus. A compact abelian path-connected matrix group is isomorphic to a torus. The proof is given by the exponential. So the exponential goes from the Lie algebra to G. That's a surjective homomorphism. Now, the reason that's surjective has to do with the compact, the path-connected matrix group, right? Am I using abelian? Yeah, well, the surjective, the exponential is not generally surjective homomorphism, so I think I'm relying on some earlier discussion here, which I don't think I've included in these talks, but that said, the kernel of the exponential is just this lattice here, this integer linear combinations of v1 through vk. So the Lie group is isomorphic to G mod the that lattice, but of course that is by what we just talked about a second ago, the k torus crossed Rd minus k. It's also not immediately obvious to me why the exponential's kernel has this form, but I'm going to go along here. But since G is compact, this piece can't be there because that's not compact, right? So this forces D to be, this has to be gone, and basically K has to be equal to D by the assumption of compactness. So again, I'm skipping some details is what I'm confessing to here. See page 139 to 140 for the details of this proof. Theorem 9.6. Any abelian path-connected matrix group is isomorphic to a k-torus crossed with Rd minus k with respect to addition. So you got these two pieces to an abelian path-connected matrix group. You have this torus, and then you have this sort of copy of just Euclidean space under addition. And so that's up to isomorphism. That's what a matrix group, a path-connected abelian matrix group, looks like. So let's let G be any matrix group. A torus in G, what is it? It's going to be a subgroup of G which is isomorphic to a torus. A maximal torus in G is simply a torus in G which is not contained in a higher dimensional torus. The fact that there has to be such a thing is essentially immediate from the fact that if you just have the matrix, just the identity itself, that's a zero torus, and the n torus has dimension n, right? So dimension G is the largest possible dimension for a submanifold of G, and so that pretty much you're looking at finitely many possibilities. There has to be a biggest one. So here's a theorem about the maximal torus, some of our favorite examples. So the maximal torus in standard example matrix groups. First of all, the maximal torus in SO2M, so an even dimensional special orthogonal group. It's just like that. The diagonal. And so a little, not sure what this R notation is. Alright, well, I should look that up. On the other hand, for the odd dimensional special orthogonal group, the maximal torus picks up this extra little one here, right? Like that. For UN, the maximal torus is just just EI theta 1, EI theta n. Those kinds of diagonal matrices with, every time here theta is taken from 0 to 2 pi, not included. The maximal torus in the symplectic group of order n is the same as the UN, right? And then the maximal torus in SUN, it's almost the same, but then this last one has minus the sum of all these guys, right? So this last angle depends in a somewhat simple way on the first n minus 1 of them. All right. So this is the standard maximal torus of these standard examples, respectively, each one. The proof is given on page 143 to 144 of TAP, where we also discover that proposition 9.9, if G is, either SON, UN, SUN, or SPN, the special orthogonal, the unitary, the special unitary, or the symplectic, and if T is the maximum torus of G, then any element of G which commutes with all of the torus must lie inside the torus itself. In other words, the torus is the maximal abelian subgroup of G. So the result above makes calculations of the centers of the matrix groups listed above a pretty simple calculation. Let's see how. So, simple enough that I've assigned it to students before who didn't know better. So the center of SO2M is I minus I. This is the group of order 2. The center of the odd dimensional special orthogonal group is just I again. The center of UN is just this. The center of UN ends up being U1 isomorphism. The center of the symplectic is again the group of order 2. The center of the special unitary group of order n is a little bit more interesting. It's the cyclic group of order n. All right. Again, you can note that the center of SUN is the center of UN intersect with SUN itself. So this intersected with SUN gives you that. And well, I mean, just in case you don't know, the center of G is the set of G in G, which commutes with all other X in G. So it's elements which commute with everything else. Let's see here. I'm not sure if we're going to say more about that theorem or not. Let me see. Nope. I left it to you guys. Another comment we can perhaps appreciate at this point. You may recall that SU2 and SO3 are isomorphic as the algebras, but here's proof positive that they're not isomorphic group. Two groups that are isomorphic certainly have the same center, so that's one of the things that you could prove in your basic group theory course without too much trouble. But as you can see, the center for SU2 and the center for SO3 are not at all the same, right? The center for SU2, it's the cyclic group of order 2. The center for SO3 is just the identity. So it's a group of order 1, it's a group of order 2. Those are not the same thing. All right. See page 145 for a discussion of why SUN cross U1, the direct product of SUN and U1, is not isomorphic to UN, despite having isomorphic Lie algebras. And here's the kicker: not only do they have isomorphic Lie algebra, there is in fact a diffeomorphism for UN and SUN cross U1. So, but it doesn't respect the Lie group structure somehow. All right. That brings us to discussion of conjugates of maximal tori. So what is that? How's that go? If T is a maximal torus of a matrix group G, then for any G in G, the conjugate of the torus, GTG inverse, is also a maximal torus of G. So they're like, I think of a torus like a donut, and so this is like some sort of picture of, in the Lie group G, there's like this like family of donuts that fill the whole space somehow. I mean, we're not quite there yet, but we've just shown that if you conjugate a torus, you get a torus again, right? So the standard maximal torus is not normal. Hence, I mean, normal in the technical sense of normal, which means that it would be a normal subgroup if GTG inverse was the same thing again. But it's not. All right. So that means that this is a new torus, which was not the standard maximal torus that we stated in the theorem. And so as G varies, this conjugation, GTG inverse, fills out all of G. In particular, I mean, we can be more precise. If G is one of these standard examples, SON, so the special orthogonal, the unitary, the special unitary, the symplectic groups of order n, and T is the standard maximal torus of G, then for each X in G, it's contained in a particular torus, which we can obtain from our canonical tori by conjugation by a particular G. All right? So application of this would be, if X is in G, then R sub X is a mapping from Kn to Kn. It's represented by a matrix, Gx, G inverse in T with respect to some basis, right? Orthonormal basis. And if we dig into the details of this case by case, what happens? Well. Oh my goodness, I keep hitting my head on this piece of wood I got up here. If I have G equals to SO3, and I let X be in SO3, then there exists a special orthogonal matrix 3 by 3 for which Gx G inverse is equal to this. Because that's the standard. This right here is the standard maximal torus in SO3 from that theorem. And so this gives me that Rx beta beta is Gx G inverse. Consider then if I take E3 times this, I get E3 again because E3 is fixed. So that tells me what? It tells me that E1 times Gx G inverse is this times that, which is cosine theta E1 plus sine theta E2. Alright, so there's E1G acting on X. Likewise, E2G acting on X gives me this. Alright, therefore, just like my Math 321 class learned in homework this semester, every element of SO3 represents a rotation because the formulas we just derived are a rotation. E3 goes to E3, E1 goes to this cosine sine, and E2 goes to this minus sine cosine. That's exactly a rotation in the E1G, E2G, E3G basis. And so that shows then that every element of SO3 represents a rotation. Let's see, let's look at the corresponding sort of argument for SO5. For SO5, if you have, excuse me, y is in the maximal torus, then Ry is going to be mapping from R5 to R5 that rotates by theta 1 vectors in this span and by theta 2 vectors in that span. And it fixes E5. That's just the canonical standard torus, okay? Say, well, why didn't you fix the first thing and then rotate like 2 and 3 and 4 and 5? Well, it's just a choice of notation. It's just a choice of notation. Our canonical tori are just, you know, it's just a choice. So, likewise, if X is an SO5, then there exists G such that Rx beta, you know, you can change basis to get back to the standard torus, right? And so with that understanding, when you work through the details, you get that for this W1 being this span and W2 being that span, W1 and W2 are perpendicular, and every element in SON, well, every element in SO5 then can be looked at as it's rotating this to itself, that to itself, and it's fixing E5G, right? And this same kind of argument can be given for SON to show, as we claimed earlier, every element in SON represents a simultaneous rotations in families of orthogonal planes. That's what it is. It's just rotations upon rotations upon rotations. And similar comments apply to the other standard matrix groups because of this maximal tori result that we have. So, where am I? So the proof of the theorem 9.1.9.13, which was what? What was theorem 9.13? 9.13 is this theorem, this innocent-looking theorem that every single element of these guys is on a torus, which is related to the maximal torus, the standard maximal torus, which we stated, and the other theorem by conjugation. That this theorem is not the simplest thing to prove. It takes a few pages. So I picked some highlights of things that I think are interesting from that. In particular, some of his comments about eigenvalues and eigenvectors are nice. So you have the eigenspace with eigenvalue lambda. You can, usual characteristic equation. And so we have any linear transformation from Cn to Cn has an eigenvalue. That's the fundamental theorem of algebra, right? Because the characteristic equation is a complex polynomial, and we know by the fundamental theorem of algebra it has n solutions, hence there exists a solution at least, so there exists an eigenvalue, and consequently an eigenvector. And then this proposition 9.15 is also very pretty. For every A in UN, in the unitary matrices, RA has an orthonormal basis of eigenvectors. I think last time I taught linear, I proved this from, as we studied, what is it called? The theory of adjoints and all that, and it's essentially this. But here it is very pretty, the way the argument is given in TAP. And I think it's the same argument we found, we looked at in linear last year, but maybe not. That part of the course is a little bit hurried, unfortunately. But anyway, so basically, let me just get to it. You should look at the proof of proposition 9.15. It gives you a way to prove this well-known result, which is not the easiest thing to prove if you just just sit down and try to prove this from scratch. It's kind of beastly. Anyway, here's a sketch of a proof of it. Finally, I'm going to start and stop again here.